All right, so next up we have Peter Hastings from Kairos. He's going to provide a commercial perspective on their activities. So looking forward to your talk, Peter. You have the floor.
All right, thanks very much. It's never good to be between the audience and lunch. It's even worse to be between the audience and happy hour, so I'll get through this as quickly as I can. Thanks for the invitation. I'm pleased to be here and to share an update on Kairos Power, or an introduction for anybody that may not be familiar with our team. I'm Peter Hastings. I'm the Vice President of Regulatory Affairs for Kairos Power. My team's responsible for NRC licensing, quality assurance, probabilistic safety analysis, and government affairs. A little bit about me: I've been with Kairos for almost 3 years. Prior to that, I was a private consultant with clients across the advanced reactor sector. Before that, I did a stint with BWX Technologies on their mPower small modular reactor, joining them after nearly 30 years with Duke Energy and Duke Engineering. So on to Kairos. We're a mission-driven company, and we like to keep that mission in front of us in everything we do. That mission, which is to enable the world's transition to clean energy with the ultimate goal of dramatically improving people's quality of life while protecting the environment, will only be possible if we think differently about nuclear and prioritize our efforts to produce a technology that's not only safe, after all, that's the price of admission, but also affordable. I'm going to talk today about the company, about our technology, and about our approach to licensing. As a quick introduction, Kairos has been around for a little over 4 years. We emerged from a DOE-sponsored integrated research project. Our co-founders who participated in that project concluded that the next logical step was to establish a private company to commercialize the fluoride salt-cooled high-temperature reactor. And if it hasn't been mentioned before, we're a solid-fueled molten salt-cooled reactor. So Kairos was thus born. In the brief time since its founding, Kairos has grown to over 150 employees, almost all of whom are focused on the technical side of the project. We're based in Alameda, California, in a repurposed World War II era hangar on the former Alameda Naval Air Station, a photo of which you can see in the slide. The lower photo was taken at our 100-employee event back when we could all congregate together. Happily, we've not missed a beat with the COVID shutdown. We are privately funded, we're singularly focused, and we're fully committed to design, license, and demonstrate this technology through an innovative, iterative development and demonstration program. Our schedule is to deploy a commercial reactor before 2030 with a significant deployment ramp shortly thereafter. As I said, our headquarters is in Alameda, and that's where the majority of our employees work. The converted hangar houses 50,000 square feet of office and lab space. Excuse me, I run the Charlotte office, which focuses primarily on licensing work. And we've opened and begun work on a new facility in Albuquerque that will house a component testing facility and engineering test unit. And finally, we have a strategic collaboration with Materion in Elmore, Ohio. Materion is the preeminent provider of beryllium fluoride. Here's a glimpse into what drives our business case. Kairos is an ancient Greek term for the right or opportune moment. For us, that moment is the upcoming retirement of a dramatic amount of natural gas fueled generating assets. We believe this will drive a huge demand, and with the urgent need for non-carbon emitting technology, we believe we can help meet that demand. Of course, that will require that we think differently so that we can, in fact, be cost competitive with natural gas. So how will we make that happen? One of the first keys to that deployment path is to establish a design with remarkably robust safety. We accomplish that with substantial safety margins inherent in TRISO fuel, which has been demonstrated to have hundreds of degrees of margin to failure as compared with our expected operating and postulated accident temperatures. We couple this with a very high very high failure tolerance of the fuel with the use of flied coolant, which, as everyone on this conference can attest to, has a tremendous affinity for radioisotopes in the unlikely event of release from the fuel form. The primary system also operates at nearly atmospheric pressure, which eliminates the volatilization component of high pressure designs. And we rely only on passive cooling for the highly unlikely accident scenarios that we evaluate as part of the licensing process. The benefit of this approach to cost is clear: a smaller safety footprint, which results in significant reduction in safety-related structure, systems, and components, directly translates to a lower cost. Most obviously, we don't require a large pressure-retaining containment structure, taking advantage instead of functional containment enabled by the robust safety margins inherent in this combination of TRISO fuel and fluid coolant. With the exception of a small set of safety-related items, the balance of the design will consist of conventional and commercially competitive equipment and materials. Incidentally, our commercial reactor is in the neighborhood of 140 megawatts electric with a core outlet temperature of about 650 degrees C. Another innovation we're incorporating comes from the concept of rapid learning cycles. It's applied in our case to challenge the conventional development cycle of nuclear with more iterative development. This approach incorporates the concept of rapid development and testing cycles, very often testing to failure as part of our prototype development. And as you'll see in a moment, this approach not only incorporates the concept of applying lessons from one test to the next, it actually applies from one physical facility to the next, which you can see in this slide. This iterative testing cycle manifests itself in a number of test platforms and facilities. The R-Lab or Rapid Lab is co-located with our Alameda headquarters and facilitates real-time prototyping concurrent with design activities. The R-Lab was commissioned over a year ago and is currently in daily use as part of our prototype testing concurrent with design. The S-Lab or Salt Lab, which is also co-located in our Alameda headquarters, was commissioned earlier this year and is actually handling molten flibe at temperature. The T facility will be used for component qualification testing. Its build out is underway in our Albuquerque facility with expected commissioning in early 2021. Not shown on this chart, but the Engineering Test Unit, or ETU, is a reduced scale non-nuclear model of the commercial nuclear island. It will be co-located with the T facility in Albuquerque and is nearing final design with expected commissioning in mid-2021. Finally, the U facility or user facility will be a full-size non-fueled copy of the commercial reactor, which not only will be useful as an operations and maintenance training facility, but will also enable us to understand with quite a bit of precision what it will take, and maybe more importantly, what it will cost to build the commercial Kairos reactor. In our development cycle, our original plan was to evolve through these test facilities from the T and U facilities directly to a commercial scale demonstration reactor. However, over the past several months, we've been evaluating an opportunity to reduce programmatic risk even further. And we've concluded the best way to do that is to deploy a reduced size test reactor as part of our development cycle. That test reactor, which we codenamed Hermes, the Greek herald of Mount Olympus, who's famous for being able to move quickly and for crossing boundaries in his role as the guide between the domain of man and that of the gods. That test reactor is currently in design, and we're very excited to have that included in our development plan. The evolution of our development program to include the test reactor is reflected here. So as we sit here today, we're well into the design of the engineering test unit, again, co-located with the T facility in Albuquerque, and we're actively working on the Hermes test reactor design. As I mentioned previously, we originally were planning to go from the engineering test unit through the U facility directly to a commercial scale demonstration reactor, which we designate here and elsewhere as KPX, X for the possibility of multiple units. Our pivot to insert a test reactor does not fundamentally change the trajectory to the commercial reactor. That is, this test reactor is in addition to, not instead of, the commercial reactor. But including a test reactor reduces our programmatic risk even further, which we'll talk about in some detail shortly. Importantly, you'll notice that, as I mentioned previously, the iterative cycle approach that we've taken to risk reduction within our test program continues beyond the initial R, S, T, and U test beds and through deployment of entire physical plants. Our development plan is one that's designed to establish cost certainty through substantial iterative steps along the way. Our development schedule doesn't simply reflect an aggressive deployment, but a fully integrated iterative development approach where the lessons learned from one iteration immediately informs the next. We're on the cusp of deploying the engineering test unit, for example, and its construction and operation will inform the design for the Hermes test reactor. You'll also notice that the full-size U facility precedes the commercial reactor, such that we will have done a tremendous amount of test driving, if you will, of the non-nuclear version in advance, not only of construction, but also startup. Here's another way to visualize how our approach reduces overall program risk. Each stage of our deployment reduces that risk in various ways. And these risks generally fall into three categories. Technical risks are reduced via iterative lab scale testing that's closely integrated with the design, plus deployment of the engineering test unit. And that risk is further significantly reduced by the deployment of a test reactor that demonstrates Kairos is capable of producing cost-effective nuclear heat. Regulatory risk is retired via comprehensive engagement with the NRC staff in advance of our actual license applications, an area where we think we're actually leading the industry. And commercial risk is retired through demonstration of the actual cost and effort to construct a full-scale nuclear island via the U facility. I hope everybody will forgive the tangent from the topic of the presentation, which is our licensing approach. But we thought it was important to provide that background. To address the licensing approach explicitly, here's a representation of our strategy reflecting not only the Hermes test reactor, but also the commercial reactor. To go from left to right, we've been in very active pre-application engagement with a number of topical reports that have been approved or are under review. The vast majority of these apply to both versions of the KPFHR design, both the test reactor and the commercial reactor. I'll talk about pre-app work a little bit more in a moment. For both the Hermes test reactor and the commercial reactor, we're planning a Part 50 construction permit and operating license. Now look, we could go all day long. We could consume an entire conference talking about the pros and cons of Part 50 versus Part 52 licensing. But suffice it to say for this point that we've picked Part 50 to enable earlier start of construction and to avoid some of the challenges of building a first-of-a-kind plant under a combined license. Downstream of the first commercial plant, we would anticipate shifting to a Part 52 process, but we're also mindful of the significant effort that's about to be launched to develop Part 53, which could change our approach. Here's an overview of our pre-application engagement. This is a very data-rich eye chart, but it's important to recognize the progress that we've made. We believe we're setting the pace in terms of active engagement with the NRC staff, and that this marks us as a serious and highly credible prospective applicant. Over the past several years, pre-application engagement, while optional, has been touted as one of the best ways to establish an efficient review of the license application itself. Apart from the obvious benefits of familiarizing the NRC staff with the design that they won't have seen before, we're also taking maximum advantage, to front load our engagement with early review of substantive topical reports to get the review of those topics in advance, as far in advance of the actual license application as possible. We've submitted 18 technical or topical reports or revisions to those reports. We've piloted what the NRC staff advertises as a no RAI approach. RAI is request for additional information to address NRC staff questions. This process consists of discussing the staff questions and incorporating changes to address those questions almost in real time without as formal and cumbersome of a letter generation cycle as we've done in the past. We've hosted multiple audits and on-site reviews back in the days when people could travel. I do have to say that the staff and both the NRC staff and the Kairos staff have responded remarkably well to maintaining progress despite the COVID-19 shutdown. We have final safety evaluations, that is final NRC approval, on several topicals, with others pending. And in some cases, those include reviews by the Advisory Committee on Reactor Safeguards. And of course, we have a number of topical reports that are still under active review, with several others teed up for submittal later this year and in early 2021. More generically, here are some of the highlights of how the advanced reactor industry and the NRC staff are addressing regulatory risk. Excuse me, and some specifics about how Kairos Power is retiring that risk, as well as technical and commercial risk. On the generic industry and NRC side, and these are not necessarily in any order, but some bright spots include the risk-informed emergency planning approach pioneered by NEI, TVA, and NewScale, and well on its way to becoming a revised NRC rule. NRC acceptance and codification of the INL produced and industry collaborated principal design criteria for advanced reactors. Commission approval of the concept of functional containment for some designs. Substantial effort begun with NGNP and evolving through the Southern-led licensing modernization project to facilitate establishment of a risk-informed safety case. A closely related hard look at the content of license applications based on that risk-informed approach. Development of the non-LWR PRA standard that will be tremendously useful in implementing the risk-informed approach. TRISO fuel qualification via DOE's AGR program and the associated EPRI topical report. Efforts underway to establish consequence-based physical security. Plans to overhaul the regulatory framework for advanced reactors via a new rule, Part 53. And commission direction to develop a generic environmental impact statement for advanced reactors. Many of the items on this list, and by the way, this isn't an exhaustive list, have really come to fruition only in the last couple of years. It's for not having much in the way of formal license applications in front of them. The NRC staff have done a tremendous amount of work, and it's thanks in large part to commitment on the part of DOE and the industry to support those efforts. On the Kairos Power side, we're taking advantage of and participating very actively in all these initiatives. We're also addressing programmatic risk in ways I discussed earlier, within our development and testing cycle through the iterative approach, with significant pre-application engagement to retire regulatory risk, with inclusion of a test reactor to retire technical risk and demonstrate the capacity to deploy cost-effective nuclear heat, with a common safety case between the test and commercial reactors, which significantly retires regulatory risk for the commercial plant via approval and demonstration of the safety case in the test reactor. With deployment of a full-size non-nuclear U facility, retiring a dramatic amount of commercial risk by showing what it costs to build the plant, and with a licensing pathway that enables the earliest deployment and reduction of first-of-a-kind regulatory risk. So finally, and I'll recognize this is a bit of preaching to the choir, as we look out over our lab facilities, I'll tee up the question, why? Why advanced nuclear? It's hard, right? So why bother? It's expensive and safety and waste and ooh, scary. But the fact is that nuclear energy under any objective metric is the safest form of energy production ever. It is available very close to 100% of the time. And nuclear is required by law to manage its own waste in a way that is virtually unmatched by other technologies. And many of the technologies that you've heard about and will hear about in this conference help close that cycle as well. Nuclear is expensive to build and cheap to operate. Large plants are virtually impossible for many markets today because they're so capital intensive, which is why Kairos Power and many of our colleagues in the advanced reactor development sector see it as a moral imperative to change that equation. And let's be clear, energy poverty is worse for the poor, at least in the short term, than climate change. The UN, for instance, lists universal access to clean energy among its top 10 priorities. They argue for transition to renewable energy in poor countries. The Breakthrough Institute argues, though, that small-scale renewable projects to supply small amounts of electricity to subsistence farmers is not effective as anything more than a stopgap because it can't address any energy poverty at scale. They say, quote, "There's no nation on earth with universal electricity access that remains primarily agrarian. Modern household energy consumption has historically been achieved as a side effect of electrification for non-household purposes such as factories, electrified transportation, public lighting, and commercial scale agriculture." I have friends who are climate change advocates and friends who are skeptics. My message to them, climate change aside, nuclear is still a smart play, and Kairos is on a mission to make new nuclear a reality. Thank you again for the opportunity to speak to you today, and I guess we'll see if we have time for comments or questions.
Yeah, Peter, thank you very much. We do have a couple questions. Very interesting presentation. Very nice to hear from you guys. First question is, what is the power level for your test reactor, and can you comment on how that affects the licensing classification?
We haven't nailed down an exact power level. It'll be somewhere in the 20 to 50 megawatt thermal range. It will not be a power reactor, so we will be licensing it as a non-power reactor, a test reactor.
Very good. And I know you still have a long way to go, but reflecting on your experience thus far, is there anything you would have done differently?
That's a good question. And I'll invite Mark Paris, who is in the audience and also presenting tomorrow, to maybe give that same question some thought between now and his presentation tomorrow. I really don't know of much I would have done differently. We purposely are on sort of a fail fast, fail forward mentality. And so we're going through development cycles all the time and informing the next iteration from the success or the failure of the prior iteration. So I probably wouldn't have planned the COVID shutdown, but other than that, I'm not sure there's much that we would change fundamentally.
Okay, one last question. So you guys are a solid fuel reactor, and looking at TRISO fuel. Now, it was mentioned earlier that other facilities are also, other technologies are interested in the TRISO fuel, be it gas-cooled reactor, maybe space reactors. How do you see the speed of that activity affecting you? Do you think it'll be in time? Or do you have a comment on how soon you think that might occur?
So another good question. There's competition sort of across the board for HALEU feedstock that's not unique to TRISO. In terms of the capacity to qualify and to fabricate TRISO fuel, there's enough momentum in the market in both those areas that I think it's not going to be what holds us up. I think that the qualification through the AGR program, we're well within the AGR parameters for our initial deployment. So that shouldn't be a tremendous concern to us, as anybody who's participated in TRISO research can attest to. The failure margins are breathtaking. We don't anticipate the production capacity being a challenge either. We've got several different pathways that we're exploring, any of which are likely to be successful.
Okay, very good. Well, thank you, Peter. That concludes the session and the day.